this inclined plane. And what I can do is, it's called an inclined plane because I can change the slope, right? I can change the angle that it makes with the horizontal. And then I have a protractor on there that I could set it, and then I could measure the angle, all right? So right now, what we've been doing is we've been looking at objects on flat horizontal surfaces. So if I just put that box on the flat surface, and then we draw a free body diagram for that, okay, it's going to look basically like our free body diagrams have. So we have our flat surface, we have FG down, and then we have the normal force up. And then normal force is equal to Fg. The friction force, if there were to be one, would be dependent on the normal force. Okay? But now we're going to change things. Right? We're going to actually raise this surface up. Okay? So it's going to be on an incline. And so basically, right now, the box stays at rest. And it wants to slide down. Right? Definitely wants to slide down. Why doesn't it slide down?
Friction.
What kind of friction?
Static.
Static friction, right? Static friction is holding it up. It wants to slide down. Static friction holds it up. If I continue raising it, at some point it's going to begin to slide. We're going to overcome static friction. And now you see the box accelerates down the plane. Okay? Now the rate at which it accelerates varies, right? If I have the incline higher, it accelerates at even a greater rate. Higher still, it's even a greater rate. If I were to bring it all the way vertical, what would be the acceleration?
9.8.
9.8, right? So basically, our acceleration is going to vary from 0 to 9.8 when it's vertical, right? And so it's going to fall somewhere in there. So while static friction is active, that acceleration is 0. When we overcome that, now there's an acceleration, and it'll vary depending on the angle of the incline. Okay. And we know that friction changes with what? When what changes, friction changes. The value of friction, right? We have the same two surfaces. We have this surface and this surface. So the value of friction is going to change when the normal force changes. So if the acceleration is changing, we know that there's forces changing. So what we want to do is learn how to draw a free body diagram for that on an inclined plane so that we could figure out things we've been figuring out, such as coefficients and velocities, etc. So on the inclined plane is what we want to look at today. And I suggest you keep notes for this because you're going to need it for the lab and for the problems we're going to do. And it can be pretty confusing, so we're going to try to nail it, make it really clear right now. So instead of having an object on a flat surface, let's do this. We'll set it up this way. So there, we have our box on the inclined plane. It's at equilibrium. And my goal is to draw a free body diagram for the box on the inclined plane at equilibrium. So first thing is, let's put in a nice big incline here. So there we go. And now that's going to be at some angle to the horizontal. We'll call that angle theta. So that's our situation, and the dot, of course, is going to represent our object. Okay, now, let's try to figure out what forces are on the box. Somebody give me a force on the box. Gravity, which way? What? Straight down, right? Gravity's always straight down. So let's put gravity down. Okay, so there's that. Of course, we'll label that Fg. So gravity is definitely pulling down on the box. What else is on the box? What other forces?
Forces of plane.
Which way is that?
I guess it's
More like this. So like this?
Yeah.
So the plane is pushing up on the box. A surface can only exert perpendicular to itself. So what am I actually going to label that? Fn, right? That's the normal force. And there's one more. Well, it would be. You know, any force could be thought of as the equilibrium. So right now, if there were only these two forces, it would definitely be accelerating. So what is that third force that keeps us in equilibrium? Static friction. Which way? Right, it's going to be this way. So static friction is actually holding it up. It's preventing it from sliding down. So that's the static friction force. And so if I were to add those three forces, what's the sum total? 0, right? It's in equilibrium. So just to clarify what Josh had said there, any force can be thought of as the equilibrium of the other two, right? To tie it into what we're looking at. All right, so now, those are our forces. Now, before, when we were on a level surface, you don't have to draw this part. Let's say we had a box and we were pulling at an angle with some tension. And the box was at an angle. The first thing we would do would be we would find our components. Because the way we solve things is to put everything on either an x-axis or a y-axis, right? And then the acceleration takes place either along x or y. So we would find components using the trig functions. So what we're going to do is, similar to this, we're going to do the same thing, only now we're going to tilt our coordinate system. So our x is going to be in line with the plane, and our y is going to be perpendicular to the plane. So now our x-axis runs along the plane, and our y-axis goes perpendicular. And if that's the case, which one of those forces needs to be resolved? Which one is not on the x and the y? Gravity, right. So if I draw it here real quick, right, this represents Fg. Then we need to resolve that. We would have a y component and an x component. We would call one of them Fgy, because it's the component of gravity in the y direction, another one in the x. So that's what we're going to do. Just like here, we resolved it. Let's resolve this vector on our free body diagram into its components. So we're going to do that. We have Fgx will be perpendicular to the plane on the y-axis. I'm sorry, that's Fgy. And then Fgx needs to be parallel to the incline on the x-axis. And those are our components of gravity. And now for our intents and purposes, that's like eliminating Fg, right? And we have the x and the y components now that we would work with. And here's our right angle that we make. So we have a right triangle, and we can figure out these sides. Does everybody follow what we're doing so far? Okay. Now real quick, because some of you will make this mistake going forward, and I'd really try to kind of lock this in today so you don't make the mistake. I'm going to put this back up here, but some of you are going to make this mistake. You're going to get this far, and then you're going to draw a line horizontal here, and then you're going to bring it a line down and call this your triangle somehow, and you're going to make that the right angle. Don't do that, okay? Don't do that. What you want to make sure of is that the bottom line is always parallel to the plane, and the other line is perpendicular. So just to review it, this Fgy is going to be perpendicular, and then the Fgx is going to be parallel to the plane. And that way you're sure that you have your triangle drawn correctly. So there's your right angle. This is called Fgy. It's along our y-axis. And this is called Fgx. So just make sure of that. Okay, now, in looking at these problems, we know that we've been doing, the friction force is dependent on the normal force. And the normal force is dependent on Fg, right? And all the problems we've been doing, normal equaled Fg, but now it doesn't, right? So the normal is now not only dependent on the weight, but it's also dependent on the angle, right? So how much this is inclined in relation with the weight gives us the normal force, which then gives us the friction force. So if I wanted to find these components, because these components are actually going to be what tells me what the normal force is, because we're in equilibrium this way. So whatever FGY is what Fn is. And whatever FGX is, if we're at equilibrium, which we are, that's what the static friction is going to be. So what else do I need about this triangle to get these sides? An angle. Right? I need an angle. So this is where we'll do a little bit of geometry and get ourselves an angle. Now you don't have to write this whole thing out because it's going to make your artwork a little bit cluttered. So just follow it and then I'll give you the last piece. So I'm going to draw a line parallel here, or I'm going to continue this line. And when I do that, I form a triangle here, and that makes an angle theta, or I'm sorry, an angle of 90 degrees. So this is 90 degrees, and now let's focus in on this angle right here. We're going to call that alpha for now. So what does theta plus alpha equal?
90.
90, right? So if this is 90, and triangle is 180, that means these two must be equal to 90. So alpha is equal to 90. I'm sorry, alpha plus theta is equal to 90. Okay, we got that. Now, let's look between the black line here and the green line here. That's a right angle. Okay, so that means that if this is a right angle and alpha plus theta equals 90, then what is this angle? Theta. Okay, so our angle right here we just proved is equal to theta, because it's alpha plus theta. So now we have an angle. As long as we can measure our incline, which we can because it'll have a protractor on it, then we have an angle, and now we can relate FG to its components. So maybe just draw a theta there. That's all you really need to know. You don't need to know how to get it. It's going to always be equal to the angle of your incline. Now, what trig function will I use to get FGY? So look at my triangle. Here's the angle. FG is the hypotenuse. Cosine. Right. So FGY is going to be gotten by using cosine, and therefore FGX will be gotten using sine. So let's just write that out. So the cosine of theta equals FGY, the adjacent to theta, over the hypotenuse FG. So FGY equals your weight FG times your cosine of theta, and then sine of theta is equal to FGX over FG. So then FGX is FG sine theta. And now that's useful to us because now we know that if we're in equilibrium, then Fn is equal to FGY, which is equal to FG cosine theta. And FGX, which is equal to FG sine theta, is what's pulling down the plane here. Right? That's the x component of gravity, FGX. If we're in equilibrium, then this has to equal that. So that means the static friction is equal to Fg sine theta. Make sense? So we're going to have incline 25 degrees, a box on there, 10 kilograms. Find mu s.
coefficient, the static, is it just x over y
Yep.
in this case?
Yep.
Is it always gonna be like that?
No. We're gonna do some examples here, you'll see what's going on. It's always friction over normal, but it's gonna vary. Okay, so you find your components first thing, 89 and 41. This is your normal force. We are at equilibrium. So that means that the static friction is equal to FGX, which we found was 41. Then you just do your division to get your coefficient. 41 over 89, you get 0.47.